Greetings, respected judges and viewers. I am Nurul Najiha Madrozni, the team leader for this project titled CocoRoad From Waste to Way. The following names are my team members. We are delighted to share our research innovation on using coconut shell charcoal ash as a sustainable modifier for bitumen. Coconut is widely used in Malaysia, but its shells often end up as agricultural waste. Improper disposal leads to environmental issues, such as landfill accumulation and carbon emissions. At the same time, bitumen performance in tropical climates often suffers from poor temperature resistance, causing rutting and cracking. Another concern is cost. Road construction can exceed Rm 1 million per kilometer, making innovation crucial. Therefore, there is still limited research on using coconut shell ash as a bitumen modifier locally. These challenges became the motivation for our work. We proposed a simple yet effective idea: use coconut shell charcoal (CSC) ash to modify bitumen. This approach converts waste into a valuable construction material. It enhances the physical properties of bitumen, improves temperature resistance, and reduces both environmental impact and cost. In short, CocoRoad transforms agricultural waste from waste to way. The objectives of this study are: first, to investigate the effect of CSC with different fineness levels on bitumen's physical properties. Second, to determine the optimum content of CSC ash for modified bitumen performance. The CSC ash was divided into three particle size ranges: CSC1 less than 75 micrometers, CSC2 between 75 and 150 micrometers, and CSC3 between 150 and 300 micrometers. We prepared samples by replacing bitumen at 0%, 10%, 15%, and 20% by weight. Laboratory tests included penetration, softening point, and viscosity. The base material used was bitumen 6070 pen combined with CSC ash. The penetration and softening point tests were conducted to evaluate how the addition of coconut shell charcoal ash, or CSC, affects the consistency and temperature resistance of bitumen. The results show a clear trend. As the percentage of CSC increases, the penetration value decreases, while the softening point increases. This means that the modified bitumen becomes stiffer and more resistant to deformation at higher temperatures. Among the samples, CSC1, with a size below 75 micrometers, showed the lowest penetration value of around 30 and the highest softening point about 51 degrees Celsius. These findings indicate that finer particles provide better dispersion and stronger bonding with bitumen, leading to improved thermal stability and rutting resistance, which are crucial for tropical climates like Malaysia. Results show that all modified samples had higher viscosity than the control sample. At 135 degrees, the control bitumen measured 403 centipoise, but with 20% CSC replacement, viscosity exceeded 800 centipoise across all particle sizes. Among them, CSC1, the finest ash, gave the highest viscosity at both 135 degrees and 165 degrees. Higher viscosity indicates better resistance to rutting at high temperature for roads in tropical regions. Comparing particle sizes at 20% replacement, finer ash clearly performed better. The CSC1 sample achieved the lowest penetration value, 30, and the highest softening point, 51 degrees Celsius. Its fine particles, about 530 nanometers, allowed better dispersion and stronger interaction with the bitumen matrix. Therefore, CSC1 was identified as the best performer. The benefits of this innovation can be seen in three dimensions. Environmental: it converts agricultural waste into useful material, reduces landfill, supports the circular economy, and lowers the carbon footprint by using local resources. Economic: it can reduce material cost, extend pavement life, and open new industries for coconut waste utilization. Technical: it improves temperature and rutting resistance, enhances durability, and remains compatible with current construction practices, meeting JKR specifications. To conclude, this research demonstrates that coconut shell charcoal ash can significantly enhance bitumen properties. Finer particles provide better performance, and 10 to 20% replacement gives optimal results. The innovation is technically feasible, environmentally sustainable, and economically practical for Malaysia's tropical climate. For practical implementation, we recommend using CSC1 at a 15-20% replacement level, especially in high temperature areas. L. Looking ahead, we propose several research directions: long-term aging studies using PAV testing, field performance evaluation on actual road sections, comprehensive economic feasibility analysis, and detailed chemical composition studies to further optimize the formulation. Thank you for your attention. Currently, our technology readiness level at stage 2. We're excited about the possibilities ahead and look forward to bringing this innovation from the laboratory to Malaysia's highways. That's all. Thank you.